So now let's get to finally real life applications of differentiation. And just note, we've been working with dy dx, but you know, we could be working with variables dv, dr, ds, dt, or whatever. Okay, so first example then, water in a tank. Sorry, no. Water is being collected in a water tank. The volume, v cubic meters of water in the tank after time t minutes, is given by this equation here. Find the rate of change of volume with respect to time when t equals 2. So the rate of change is the slope. The slope is dy dx, or in this case dv dt. So v equals 3t squared plus 4t plus 2. dv dt must be 6t plus 4. T is equal to 2. Plug it in, and the rate of change of the volume at that time is 16 meters cubed per minute. Which means that the tank is filling by 16 meters cubed every minute at that time. Okay. Now let's talk about displacement, velocity, and acceleration. Okay, so here's an example. S, distance in meters, is equal to 3 minus 6t plus t cubed, and t is time in seconds. Here's an example of what an equation could end up as, a formula and equation for a body, particle, whatever it is, moving along a straight line, that we can find how far it's travelled if we know time, how long it's been travelling for. For this particular body, this might be the equation that defines its speed and time. Okay? So if s is equal to all of this, then ds dt actually gives us the velocity. If we differentiate this, we will get the velocity of the particle. And if it's positive, that tells us that the particle is moving away from some point B. And if the SDT is negative, that tells us that the particle is moving towards some fixed point P. And what's even more interesting is then, if we were to find, further differentiate this to get dv dt, okay, so this is the velocity, so we can call it dv, it's the SDT, but now we can say dv dt. We can find dv dt, that's d2s dt squared, okay? So, and the change in velocity is known as the acceleration. The units are meters per second squared, and if it's negative, it's slowing down. So in other words, if we differentiate this function once, we get the velocity. If we differentiate it twice, we get the acceleration. Okay. Okay, a body moves along a straight line, and its distance s meters from a fixed point on the line after t seconds is given by s equals 3t cubed minus 4t plus 6. Find the speed after t seconds. Well, s is given by that. ds dt must be 3 3s are 9t squared minus 4. So after 2 seconds, its speed is plug 2 in for t, 32 meters per second. After how many seconds is the body at rest? So when it's at rest, it's no speed. ds dt must be equal to 0. So we let our ds dt equal to 0. So that means that t is equal to 2 over 3. And fourthly, it's just crunched in here. Find the acceleration. Well, basically we have 9t squared, 9t squared, 9t squared minus 4, so that's equal to 18t. So I'm not sure after how many seconds it's asking us there in the question. After 3 seconds, okay, t equals 3. It's in the book anywhere somewhere. So it's equal to 56 meters per second squared. Okay, so the acceleration after 3 seconds will be this. Rocket example. A rocket is fired vertically upwards. After t seconds, its height, h meters, is given by h equals 100t minus 5t squared. Find the height after 2 seconds. Just plug in t equals 2, it's 180 meters. Find the velocity of the rocket after t equals 3. Well, if h is that, velocity is dh dt, which is 100 minus 2 5s are 10, and After 3 seconds, plug in t is 3, it's 70 meters per second. After how many seconds the rocket is momentarily at rest? So in other words, when does it just momentarily stop? It momentarily stops at its highest point before it falls back down again. Okay, but at rest the speed is 0, so dh dt must be equal to 0. So that means 100 minus 10t is equal to 0. T is equal to 10 seconds. And then up here we have the max height. Find the max height reached by the rocket. Well, the max height is reached just before it falls back down. Okay, and that if you recall, was that t equals 10 seconds. So you plug 10 into your formula for height, 500 meters before it stops and falls back down again. And we'll just finish by doing a couple of examples in relation to maximum values. So if you remember that for y equals f of x, dy dx is equal to 0 at the maximum minimum turning points in that curve. So let's make use of that fact. Question 5, page 542. The length of the rectangle is x centimeters and its perimeter is 12. Show that the area is 6x minus x squared. Well, the way to do that is to draw the rectangle x and y, and note that 12 is equal to this plus this plus this plus this, or 12 is equal to 2x plus 2y. Divide everything by 2 there and you get 6 equals x plus y. So relate x in terms of, y in terms of x, y is equal to 6 minus x. And if y is equal to 6 minus x, and that's y there, or 6 minus x, then the area is x by this side. So the area must be x by y, x by 6 minus x. The area is equal to 6x minus x squared. So that proves that bit there. For what value of x is the area of the rectangle at maximum? Well, it's at a maximum when dA dx, this is a, so the function a, so dA dx is equal to 0. So if a is 6x minus x squared, then dA dx is 6 minus 2x, okay? And all that's equal to 0, which tells us that x must be equal to 3. Okay, so that's the value of x, which the area is at its maximum. Now, we did meet this type of problem when we were doing real-life examples of functions, but as far as I recall, we may have been plotting the function wrong. We weren't using differentiation anyway. So there's two ways to come at these problems: graphing them and differentiation. Okay, so find this area then. Well, if x equals 3, simply plug it into the area formula. Area is 9 meters squared. Now, I haven't written out this question, but it's in the book, question 7, page 542, about a farmer, has a field, has big fields. He produces wheat, and the yield per hectare of wheat is given by the function 7,000 plus 32n minus 0.1 times n squared, where n is the amount of nitrogen he uses. So how much wheat will, if he uses 100 kilograms of nitrogen, is he going to get? Well, y equals, plug 100 into there, that's how much kilograms per hectare. How much nitrogen to get the maximum out of his field? Well, y is equal to that. The maximum is first of all, we need to find dy dx first, and we get that's equal to 32 minus 0.2n, and at maximum dy dx, turning point, minimum point, dy dx equals 0. So 0 is equal to 32 minus 0.2n. So n must be equal to 160. 0 equals 32 minus 0.2n. So minus 32 equals minus 0.2n. So n is equal to 32 over 0.2 minus minus, they'll cancel anyway. N is 160. That's where that came from. Okay. Now, what's the maximum yield per hectare? Well, 160 is the magic number for n. Plug that into the main equation, you get 9560. And now, it costs him 1,300 to do the work, but he can sell for 160 per ton. How many tons has he got? Be careful, 9.560 tons. Okay, there's 1,000 kilograms in a ton. So if he's got 9,560, he's 9.56 kilograms. Okay. So he can sell for 160 per ton, and also he makes 75 per hectare. Okay, so the profit is 9,560 tonnes by 160 gives us that, plus 75 per hectare gives us 1604. Take off your 1300 his costs, and you get his profit of €304.60 per hectare.